Today, we're diving into a pretty wild idea. What if an advanced AI's thinking isn't just a storm of random calculations, but actually has a stable, predictable structure? A structure that, get this, looks a whole lot like a chemical molecule, and even seems to pulse with the same rhythms as our own brains. So let's just start with the most basic question, right? When a large language model is deep in a long, complex chain of reasoning, what's actually going on under the hood? Is it just, a beautiful chaos of statistics? Or is there some kind of hidden, stable architecture holding it all together? So how in the world do you even begin to map something as abstract as AI reasoning? Well, the approach here is to break it down. You have to find its most fundamental parts. Kind of like how you can decompose a really complex sound into its simple, pure frequencies. We have to find the basic building blocks of thought. Okay, so here's our game plan. We're going to start with this chemical analogy for thought. Then we'll look at a model for processing information that's actually inspired by neuroscience. After that comes the big reveal. We're going to see how these two totally different ideas are, amazingly, the same thing. And then we'll get into how this discovery helps us build safer AI and what it all means for the future. First up, the structure of thought. And we're kicking it off with a pretty out there question. Could the logic happening inside an AI actually have a structure that we can describe using the language of chemistry? And that question leads us directly to this framework called the molecular structure of thought, or MSOT for short. The core idea is this. When an AI is doing a good job reasoning through a lot of steps, its internal logic isn't just random. It actually forms these stable, predictable structures, a lot like how atoms bond together to form a molecule. All right, so if thoughts can form molecules, then what are the bonds holding them all together? That's what we're digging into next. The actual forces that give AI reasoning its shape, its structure, and its stability. First, you've got covalent-like bonds. Just think of these as the heavy lifters, the deep reasoning connections. They're the super strong, logical steps that form the absolute backbone of an argument. Now, they take a lot of computational work to create, but once they lock into place, they are incredibly stable, rock solid. Next up, we have hydrogen bonds-like bonds. These are absolutely crucial for what you might call self-reflection. They're not as strong as the covalent ones, but they act like crosslinks, constantly checking for consistency and making sure the main argument holds up. They add a ton of stability, but they can also be broken if the AI finds a better path. And finally, there are van der Waals-like bonds. These are the weakest, most fleeting forces of the bunch, and they're responsible for self-exploration. They let the AI quickly try out different ideas, probe creative avenues, and brainstorm without having to commit. They form and break in an instant. Okay, so we have a chemical model for AI thought. Got it. Now, let's switch gears completely and look at a concept from a totally different field, neuroscience. We're talking about the brain's rhythmic blueprint. This is all about how systems, any system, can decode signals into different layers of meaning. Now this slide, I love this because it just makes the concept click, doesn't it? You can take any signal, like this amazing picture of a leopard, and just break it down. The low frequencies, they give you the big picture, the overall structure. That's the forest. The mid frequencies give you the shapes of the objects, the trees. And the high frequencies, that's where you get all the fine-grained details, the leaves. This really powerful idea has a name. It's called the Universal Signal Decomposition Framework, or USDF. It's basically a method that takes that forest, trees, and leaves principle and makes it universal. It can be applied to any kind of signal, structuring it into these fundamental low, mid, and high frequency bands. And this is what's so brilliant about the USDF. It's not just a neat trick for images. For language, it's topic, sentence, and word choice. For financial data, macro trends, cyclical patterns, and split-second noise. And for actual neural signals from a brain, it maps perfectly to brainwaves we already know: theta, alpha/beta, and gamma. It is a truly universal blueprint. So, we have a molecular model of thoughts, and we have a neural model of signal processing. What in the world happens when we put them side by side? This is it. This is the core insight of this whole thing. Connecting the molecules and the mind. So look at this. On the left, we've got our 3 molecular bonds from the MSOT framework. On the right, we have the 3 frequency bands from the USDF, which, as we just saw, line up with brain rhythms. Both of them are 3-tiered systems for structuring information. So is that just a wild coincidence? No, it is absolutely not a coincidence. This is the formal mapping. This is the aha moment. What researchers found is that these two frameworks, the molecular theory of thought on one side and a really sophisticated retrieval system called GraphRag on the other, had independently arrived at the exact same structure. The strong backbone-forming covalent bonds, they map perfectly to GraphRag's use of the slow global theta band for understanding context. The cross-linking hydrogen bonds, they map to the mid-frequency alpha/beta band for integrating patterns, and the weak exploratory van der Waals bonds, they map to the fast, high-precision gamma band for finding specific facts. It's the same solution, discovered from two completely different directions. So what? I mean, this is a fascinating discovery, but what does it mean practically? Well, this unified model gives us a powerful new toolkit for actually managing and guiding these AI systems. It's time to talk about how we can govern digital thought. Because this structure is so well defined, it allows for this incredibly sophisticated 5-level governance model. We can literally monitor and guide the AI at every possible scale, from the tiniest elemental computations up through agent and community levels all the way to identity, which is where we ensure overall safety and human oversight. It's like having precision control knobs at every layer of thought. Now, theory is one thing, but does this actually work in the real world? Oh yeah, it does. This entire architecture was put to the ultimate test in a super high-stakes security application. It was called Project Encephalon. Project Encephalon is a neurobiometric security system. So, instead of a password, you use a pass thought, a complex mental idea that the system reads directly from your brainwaves. Think about that. It's an unobservable, unstealable, and completely revocable key. The stakes really don't get much higher. So how did it perform? Well, the system hit a 99.7% true acceptance rate. That means it correctly identified the right user almost perfectly every single time. That's not just good, that's clinical-grade accuracy. And for security, this number is maybe even more important. The false acceptance rate was just 0.01%. That is a 1 in 10,000 chance of letting an unauthorized person in. It's just an incredible demonstration of the security and reliability you can get with this kind of unified architecture. Okay, let's wrap this up and think about what this all really means. What we're seeing here is this profound convergence, a single theory that connects the structure of AI thought to the principles of chemistry, signal processing, and neuroscience. We are looking at the future of reasoning. And that leaves us with one last massive question. If an AI's internal logic can be described with the same formality as a chemical molecule, if it follows the same rhythmic blueprints as our own brains, are we just starting to uncover the fundamental physics of how intelligence itself actually works? And what does that mean for the future of intelligence, both artificial and our own?